Every year, people from around the world flock to remote northern latitudes and regions such as Norway and Alaska to witness a breathtaking natural phenomenon called the Northern Lights. The scientific name is Aurora Borealis, and the science behind it is intriguing to say the least. When discussing it, physicists often rush to explain how it's caused by charged particles hitting the Earth's atmosphere at high speeds. Or they'll describe how the magnetic field of the Earth produces the dynamic shapes in the sky. And they're not wrong, but in my opinion, the most important thing to discuss is the color. That's right, the color. And we can explain it using chemistry. So why do we observe specific colors in the Northern Lights? This is actually due to the elements nitrogen and oxygen present in Earth's atmosphere. Depending on the altitude, oxygen concentrations are responsible for either the red or the green color that we see. At low altitudes, there's less oxygen, and the presence of nitrogen in the atmosphere is responsible for some of the reds and the blues that we see. But how can elements like oxygen or nitrogen be responsible for color? From a young age, we're often told that white light is made up of all the colors of the rainbow, like my background is here. What we're really talking about is the region of the electromagnetic spectrum that corresponds to visible light. If we put on these diffraction grating glasses, which are really just modern-day prisms, the white light that passes through them breaks into its contributing colors. I'll turn off the light so you can see what I really mean. As you can see, we get something that looks like a full rainbow. Okay, I'll bring the lights back up. You'll sometimes hear the acronym Roy G. Biv to name the colors of the rainbow. Well, that's actually each color's relative place on the visible part of the electromagnetic spectrum. Now let's replace this white light with a hydrogen light. Here, we need a tube filled with hydrogen gas, and we can apply a high voltage to see what happens. I'll turn the lights down again. We'll need to put our glasses on. If we examine the photons emitted by a sample of hydrogen atoms, we observe that hydrogen only emits photons corresponding to a few very specific colors: a red line, a blue-green line, and two purple-violet lines. Okay, I'll bring the lights back up. So why does hydrogen only emit photons in these particular colors? To understand that, let's consider what the color of a photon signifies. The energy of a photon is directly proportional to the frequency of the corresponding light. We represent this with the equation E equals h nu, where h represents Planck's constant, a value that helps us link the frequencies of photons to their energy. Using the frequency of light represented by nu, we can calculate the energy of the corresponding photons. For example, let's focus on how the red color emitted by hydrogen corresponds to photons with a specific energy. Because we're applying a high voltage, the electrons in the hydrogen atoms begin at an excited state. When the electron relaxes, energy must be conserved, so a photon is emitted. Let's visualize this with a diagram. The hydrogen atom begins with an initial high energy, and after the photon is emitted, the atom has a final energy that's lower. The difference between the initial and final energies corresponds to the energy of the emitted photon. Now we know that the energy of the photon is equal to the electron energy gap within the atom. But why would the atom only emit photons with very specific colors or frequencies? The answer lies in the fact that electrons within atoms can only have specific energy levels. The emission of a photon with this energy is allowed because both the initial and final electron energy levels are permitted energies within that atom. However, if we consider the emission of a photon with the energy shown here, this would not be allowed because these electron energy levels are not permitted within this particular atom. The discovery of these quantized energy levels led to the development of quantum mechanics, which provides the laws of physics that we now use whenever we work at the atomic scale. The spectrum of hydrogen arises from quantized electron energy gaps that lead to the emission of photons in the visible region of the electromagnetic spectrum. The energy levels in hydrogen are different from those in all other elements. Therefore, hydrogen is the only element that emits this particular pattern of visible lines. Its spectrum is unique, like a signature or a fingerprint. In fact, each element has a unique spectrum, which can be used to identify it. Let's take a look at some other elements. I'll bring the lights down and we can put on our glasses. This is neon. And this is mercury. In the aurora borealis, we saw red, green, and blue lights. The emission spectra of oxygen and nitrogen are all shown here. Where else can we see the emission of specific elements? If you guessed fireworks, you'd be right. Different elements are utilized in fireworks to create the wonderful range of colors that we see from them. So the next time you look up into the night sky to enjoy a fireworks display, or if you're really lucky, the northern lights, you'll be able to appreciate how chemistry can explain the awe-inspiring colors.